marche ou pas?
Je pense. Comment je peux minimiser ça?
Oui, mais si c'est bon, l'écran, c'est très bien.
You can also hide the bar.
Oh.
I don't know enough French to.
How can I?
Well,
it's okay. Okay, it's okay.
okay, we don't care the bar.
No, we care the bar. How can I get rid of the bar? The dots?
I think it says.
Masquer.
Masquer le volet vidéo. Masquer le volet vidéo? No, it's not masking the bar.
Comment c'est? Putain, c'est tout pourri.
It's not masking the bar though.
Désolé.
Get me rid of that. Got it.
Son information. My name and annotation, tu vois ça?
No. Can't get rid of the bar. J'aurais dit
Maybe it's just this one?
this one?
Yeah.
No,
Nope.
doesn't want to.
Tu peux le mettre tout en bas sinon?
Tout en bas, I can't, but that's okay. Well, we have a bar. Otherwise, I stop sharing the screen some. Okay. Sorry for that.
Sorry.
You told me to. Attends, on va arrêter ton truc. Écran, joindre. Ah oui.
Tableau.
He wanted me to clone the screen, but then cloning was not. What?
But I was plugging it in.
Yeah, here now I can. But then
We stop sharing, and then the bar will be the screen.
De-
La barre, et
Attends,
puis
tu veux-
déplacer.
Ah, tu, je sais pas où est ma souris, moi. Je l'ai perdu. Ah non. Et voilà.
Et voilà.
OK, et voilà. Oh! Thanks a lot. This is it. That's okay. Okay, so thanks a lot for the invitation and for the Zoom help. So yeah, today I'd like to talk about spike sorting, bringing the spirit of a modular and collaborative approach. So that's a work that we initiated with Sam. And as you might have thought just with the previous talk, I mean, you have a lot of labs working on spike sorting IDs and pipelines, and there are some good ideas here and there. And the idea would be to try to think about combining all of them, because so you heard already quite a lot about spike interface in the previous talks. And if you're attending the tutorial session tomorrow, you'll hear more about it. So spike interface started as a beginning as a project to properly benchmark spike sorters back in 2020. It was something that aimed at unifying and standardizing the way people were handling the recordings and the spike sorting results. So you had the raw data, then it was conceptualized as a recording, and then the black box here was the spike sorters, could have been kilosort or something else. And back in 2020, in this eLife paper, I will try to hide this, but no. Alessio and others compared the results of various spike sorters that were available at that time. I won't go through the names, but the take-home message at that point was that they were strongly not agreeing across each other. And that was the first puzzling results. Thus, the idea was to try to see how we could unify them and try to understand who is right and maybe in which situation and so on and so forth. Spike interface kept growing over the years, and now it's becoming quite a very large collaborative project, and it extended quite importantly, actually. It can read many file formats and handle also probe geometry, and now it's allowing you to design spike sorting pipelines in a fairly easy manner. So there was a huge focus put on the pre-processing tool pipelines, how to filter, remove some artifacts, median reference, and so on and so forth. Motion correction, that was just talked about before by Charlie, is one of those very complicated pre-processing steps that is now kind of a key for human or neuropixel recordings in vivo. You still have a black box here. I mean, once you have your data that have been pre-processed, you gave them to a spike sorter. And here you have various flavors depending on your habits, your labs, your knowledge, I mean, maybe you use QSort 2.5, 4, spiking circus is one of the sorter also I developed a while ago. And once you have these results coming out from this black box, thanks to Spike interface, you can then easily now compute standardized quality metrics. And at least we know that we're all talking about the same quantitative measure because there is kind of documentation, they have been validated, tested, and then you can curate your data. And if you want, export for file, or now also Spike interface is handling quite intensively the visualization of the output of the spike sorting result themselves, thanks to IPy widgets in notebooks and sorting view also developed by Sam and Sigui and so on and so forth. So the spike sorting view is by Jeremy Maglan at the Simons Foundation, and the Sigui, the spike interface GUI, thanks to Sam. But so the whole ecosystem has grown quite extensively, and the idea is to ease the development of pipeline. But we still have this black box here in a sense. So Spike interface can handle modularity for pre-processing, and that's really convenient. And those operations can be achieved in a lazy manner. They are memory efficient, they can be parallelized, and so on and so forth. So now the typical pipeline in most of the lab is to use Spike interface to handle the pre-processing, or it could also be achieved thanks to Spike GLX, but like, for example, filtering, removing the median, and giving this data to Spike sorter, one. Or you can do some phase shift, maybe if you're using some NeuroPixel and you want to compensate for the sampling, or you can also eventually correct for motion. Like, for example, Charlie just presented a method that might outperform the one from Kilosort. So you wish you would be able to still use that. And maybe if you want, plug that into Kilosort, turning off the motion correction method of Kilosort and using the one implemented here by Paninsky group. But in all those pipelines, we still have those black boxes here. And the question is, why stopping here actually? Because now we have a very nice modularity at the pre-processing stage. The field of spike sorting has also matured enough among developers to kind of identify what are the key steps of the spike sorter. So why not try to open the box actually? For example, back in 2018, I developed Spiking Circus 1 that was published in eLive back then. And at the end of the day, Spiking Circus can be summarized in kind of some pre-processing operation that could be achieved easily by a Spike interface, filtering, CMR, local whitening. You do have a peak detection step. You select some of those peaks, you perform a clustering, and once you have a dictionary of templates obtained after clustering, you launch what's called a template matching step. The details below the boxes are the way they are implemented, but conceptually, those are the steps of the algorithm. And at the end, we had some sort of heuristic meta merging trying to reconstruct the cells. If you look at Kilosort 2, the general ideas are somehow similar. You have the same pre-processing steps, although if you look closely, they are not performed in the same order. So this is already a question we might address. I mean, why and what's the best? No one actually has properly tested that, but so they are done in different orders. There is a peak detection step implemented in a different manner. So and we'll come back to that afterwards. The clustering step also is a bit different. And the deconvolution step, which is the template matching in a sense, is also a bit different. And at the end, you have some merge split, which kind of would be in line with this meta merging with a bimodality pursuit that try to reconstruct the cell to have as complete representation as possible. Kilosort 2.5 builds upon Kilosort 2 and add an estimate and correct motion drift here step as a pre-processing step. This is the major improvement here. And as Charlie already explained it before, this is with a unique template and some centralized approach of correcting for motion. And you have the same, the rest of the algorithm is similar. I won't talk about Kilosort 3, but Kilosort 4 mostly refines again. So the same pipeline here is kept constant. The clustering is a bit different here. I won't go too much into the details, so I won't have time during the lecture here to go into the core meat of the algorithm. But so let's say the clustering is a bit different. And at the end, the reclustering, so the merge sleep step here is also improved and consolidated in kilosort 4. Those are the main differences here. But so in all those cases that I just aforementioned, we can see that those pipelines can be summarized as follows. So we have a pre-processing steps, some peak detection. Clearly, we need to know where the information is in the signal. Eventually, we need to select some of them because we can't cluster from all those peaks in the recordings are so large nowadays. We need to cluster to get some templates. And once we have those templates, we need to reconstruct the signal as a linear sum of those templates with some mathematical steps called a template matching or deconvolution, you name it. And at the end of the day, when we have explained our signal as a linear sum of templates, we need to maybe do some meta merging or cleaning to consolidate, and maybe some cells have been splitted, so we need to group them all together and so on and so forth. So this pipeline is, I would say, fairly robust across all modern spike sorters, spiking seekers, kilosort, yes. There are some tricks here and there and some good ideas. And the question is, how can we combine good idea there and good idea there and have something that maybe, hopefully one day will rule them all? Because currently nowadays, no spike sorter pipeline will be guaranteed to work out of the box for all the data in all the species, animals, probes, and so on and so forth with the given set of parameters. So no one knows what's the best outcomes. So what we started to do with Sam and other colleagues here is to try to implement some of the options all across this pathway. So for example, for pre-processing, that's what have already been started in Spike Interface. Now, Spike Interface is a huge library of pre-processing steps that are the most commonly seen, used nowadays. Why not extend this approach? So peak detection, various choices can also be made. And we implemented two that I will talk about after in the talks. Peak selection also, we could think about various ways of selecting the peaks. Clustering, various options here can be performed. And Charlie also here just talk about one that might be interesting, but the question is, how can I know how good it is? It's worth having this step as an isolated component, having a clustering drift, being aware of the drift, and template matching steps also, two will be tested, and meta merging options. So here, this is just the beginning of the work, but I will explain you more in depth that with the sorting component in Spike Interface, we want to really extend on this pipeline such that it will be easy for developers to add methods as class, and using this method to properly answer a scientific question, because so those pipelines are complicated recipes at the end of the day. And if something goes wrong, we'll need to know exactly when it goes wrong. And to do that, we'll need to open the box and benchmark properly the steps all across the path. Otherwise, at the end, when something goes wrong, we just tweak parameters, launch, wait 5 hours, and I don't know, getting no insight about what has gone wrong and why. So the modularity will ease the maintenance, the benchmarks, the evolution, and the dissemination also. It will just allow the work to be disseminated quicker and ideas to also spread in the community. So we design kind of a benchmark. We designed this idea of benchmarking components. So we have benchmarks that will, and I will show them in the following, that will test all those steps, and then we can, at each of the steps, make several choices and take the one that seems to be the best and combine and make a pipeline as a succession of those steps, properly benchmark all across the way. This is a work in progress. Those benchmark objects that I will talk about today, I will just talk about the peak detection one, the clustering and the matching. Peak selection is work in progress, and same for the meta merging, but those are components that has to be done. All those objects, they are really easy and to create. They can launch various methods, save all the results, reload the results, make plots, provide metrics and quantitative measure about how good this step is, such that you can clearly know for a given particular data sets or sets of data, if you have a ground truth. So that's the trick here, in a sense, you can benchmark it and assess how good you are. The key feature also, and Sam worked a lot on that also before, is that to do benchmark, we need to generate artificial recording in a pretty fast manner. So now in Spike Interface, there is a new generation module that allows you to take a probe geometry, for example, your NeuroPixel layout, generate some templates. So those templates can be generated artificially with a mathematical model, or they can be taken from a library coming from the IBL dataset, so they can have real shape and morphologies if you want. You can create fake raster plots, and also you can, and that's the key point here, you can create a motion such that you will generate traces on the fly. It's really fast, it's lazy, and we think it could be a replacement for MEREC. That was a library developed by Alessio Buccino before that used to be very practical to generate drift, but that's really heavy. To generate a drift, you need to pre-compute a lot of stuff, and it's hundreds of gig just for one experiment. So here, everything is done on the fly, and it's really quick with just 2 lines of code. You can generate a drifting recordings, and you'll get a static version of it, a drifting version of it, and the spike sorting results. So if you want to assess question about how good you are sorting static or drifting, depending on the type of drift, we'll go for that. So in all the following, when I will talk about a static recording, I will mostly refer to a NeuroPixel 2 layout, restricted to 128 channels, because for the benchmarking, the algorithm, it's enough. With 250 cells in a 2 to 8 hertz for the firing, artificial templates, 300 seconds, no motion, and the generator now has also some realistic covariance for the noise level and so on and so forth. When I will talk about a drifting recordings, I will assume that I'm taking my static recording and I'm adding a zigzag rigid motion on top of it. And this will be my drifting recordings, okay? And also in the following, when I will talk about a motion corrected recording, I will take the best, I mean, up to now, I would say method for compensating for the motion. And as already Charlie mentioned before, in Spike interface, there is a correct motion function that will allow me to, given the raster plots aforementioned also by Charlie, to correct and estimate the motion and compensate for it. And as you can see, the decentralized approach published by the Paninsky group in this particular case on my data is estimating, well, it's tracking very fairly and very nicely the drift. So my motion correction data is something that I guess is the closest to what I wish I could have, but it still have some noise, maybe due to the fact that the motion estimation is not perfect, but still, let's say it's the best I can do these days. Okay, so actually, last year, no, it has been published this year, but we already started this modular approach with Sam and Alessio, because the drift correction algorithm, Charlie talked about before, but you have various ways of estimating the position of the cells, estimating the motion, and compensating for that. Kilosort is one of those options. Those are the arrow boxes. The decentralized is some others. So in Neuroelastic, we already show how this modular approach can be beneficial for the field, because in this particular case, so in this paper, we benchmark various pathways and possibilities that could be achieved. And turns out that one of the best options is to estimate the position the way Kilosort does that, because it's fast, and estimate the motion the way the Paninsky group does that, because it seems that it's easy. I mean, it's more accurate. So you already see the benefits that you have to combine the two small details of those two groups in something that then outperforms, or at least is working in a decent manner out of those. So if you want to have more details, go into this paper. So now coming back to the peak detection step, in a sense. So most of the algorithm, spiking circus 1 or some others, use to detect the peaks with some sort of locally exclusive, so spatio-temporal radius to exclude the duplicates. So we detect the peaks as threshold crossing, but in some small local spatio-temporal neighborhood, we exclude the redundant one. Kilosorts use what's called a match filtering. So if you know the shape of the templates, kind of, you can convolve all the traces with those shapes, and you can maximize the signal to noise doing so and try to enhance the detection of the small events. So let's try to benchmark that. So what's the interest of those two? So now, given our benchmark object, we can create a static recordings, filter, remove the median, whiten, and then we can test what's the best choice here that should be made. Should we detect with the locally exclusive or match filtering? What's the gain of those two steps here? In the following, I won't benchmark those steps here, but some other people in the room, like let's say, for example, Aurélien, might say that it's worth also benchmarking how do you filter the data or the order of those operations. I won't go into that, but that's also a question we might ask actually. What's the best filter? Is it worth doing the median and so on and so forth? Just comparing about that, so if we detect the peak with the locally exclusive method, so those are the ground truth amplitudes of all the peaks in my data. And in blue, this is the distribution of the found one. And I can see that, so this is the detection threshold, the dashed dot line at 5. So I don't find any peak below that. That's okay, because this is my detection profile. With the match filtering stuff, actually, you don't see it properly here, but we can find and recover some spikes that will be below the detection threshold because of this match filtering approach. So if I'm looking at the cosine, so the similarity between the templates of the cells that I have in my ground truth and the one that I've recovered, we see that indeed using match filtering is helping to recover smaller units. Here, I'm getting more smaller units. But it comes here in a cost, it's slower because I'm generating a huge amount of templates and I'm convolving all my traces with those templates. So it could be efficiently done with GPUs, but here it's on CPU. But so there is a gain, at least we can quantify it. If I'm coming now to the clustering, we can also ask the question. So spiking circuits has some clustering with spatial temporal features extracted by PCA. So because we wanted to establish some sort of a competition, even though it's a collaborative project here, Sam made some 3D clue clustering. And I also took a very simple random projection one that's suited for more online and very quick, but it's just based on spatial features. So when you have a template, you just extract the peak to peak on all the channels and you perform a clustering. I won't go into the details of this algorithm because I don't have time, but the question that I want to convey here, the message I want to convey is that who has the best clustering? We don't know, but we can benchmark. We should benchmark this step and this step only. So I can again take my pipeline, static filtering CMR, whiten my data and ask what's the best clustering. On this slide and this slide only, I will just take 32 channels for visualization because what's the best clustering is not as straightforward as you might think question to answer clearly, because a good clustering should find all the clusters, but not too many crappy or splitted or overmerged. So it's still something that can be discussed. For example, 3D clue here is you have 32, well, so the matrix, this is an agreement matrix, so is very good and squared. Circus is also good, but tend to find too many here overmerged cells. And this projection here also is really bad and hallucinate quite a lot of units. But so this is something that at least can be tested. And it's also something that was around in the literature, like, is it important to whiten the data? Is your clustering algorithm sensitive to whitening? And if so, what kind of whitening? So it's a bit technical, sorry for the biologists here in a sense. But so whitening is a way to get rid of the spatial temporal correlation of the noise in your channel. And so you have different ways of doing this step, and all the spike sorters are not doing it in the same manner. So we can at least now compare the results easily. So 3D clue benefits from the whitening here. Global or local doesn't really matter. Same for the clustering. Same for the random projection in a sense here, although this one is clearly finding much less cell, meaning the cells with slow SNR are not picked because it's not using any temporal information, so it's losing here a lot of cells. But so what we can here just conclude is that whitening is beneficial, doesn't really matter local or global. And spatial temporal feature seems to outperform just spatial one. Something that could have been guessed, but still it's worth testing it. And now we can also assess, okay, but now let's take my static recording and let's say I'm whitening it because I discovered that whiten is beneficial for my pipeline. And I will compare it to my drifting recording that will be motion corrected in the best manner I could think of those days with Charlie's method, let's say. And then I will ask how is the clustering performing now? if you look at the results, so this is a graph showing the depth and the SNR, and this is the recall, so how good your clustering is. So Circus and 3D Clue in the static case are finding quite a lot of cells. Okay, random projection here is finding less, and mostly low SNR cells are missed. Even in the drifting corrected, so the best scenario here, this Circus is more robust, but 3D Clue is collapsing, and same for the random projection. So this is the loss here showing the difference between the recall in the static versus the drifting. So this recording is not that different from the static. It's the static plus some imperfection of the motion correction step, but this is already enough to make some clustering completely collapsing. Just want to highlight this. Now, let's go to the template matching step, because here, again, these days, two different options are, let's say, available. So Circus have implemented a full orthogonal matching pursuits algorithm, mathematically solving the collision as much as it can, I would say. And there is something coming from the YAS pipeline, and it's very similar to what Kilosort is doing. Actually, it's called the wobble. We call that a wobble. Those two methods have been implemented in Spike Interface. It's a full deconvolution with temporal super resolution, actually. And Charlie helped for Atkinson to port that. So we can benchmark those two. What's the best? Which one should I use? I don't know. So again, the same pipeline, whitening or not, this is a question. And I'm providing those real templates to those two methods, and I'm benchmarking it. So again, out of the box, so this is the recall, accuracy, and precision comparing those two algorithms. So Circus or MPSVD tends to have a better recall, finding more cells, but Wobble has a better precision in a sense. So, and Wobble is a bit faster. So again, at least we can quantify those steps. Again, I will make a pipeline at the end, but I'm not here saying I have the answer to spike sorting, but we want to put the tools to be able to compare that. The two are really good at disentangling the accuracy is very good, collapse for small SNR cell, but that's expected in a sense. This approach of comparing spike sorters and template matching based pipeline it's also a paper we did again with Samuel and Alessio. And at that time, we are comparing how good the spike sorters were to handle collision. So those graphs are a bit complicated to explain, but I will go through them simply. So if you think about template deconvolution, so it's harder for the sorters to disambiguate spikes when they are synchronous, so at the same time, but also when the templates are similar. So those are the two ways of the task to be difficult. So we can look at how good we are at finding collision as function of the cosine similarity between pairs of templates. So meaning if it's dark blue, that means that for two templates that are really dissimilar, irregardless of the time lags between spikes that are colliding, so at 0 means fully synchronous, they will be fully recovered by the Wobble pipeline. So Wobble will be really good at finding colliding spikes if the templates are different. If the templates start to be really similar, you'll see a dip here. And this dip means that Wobble will miss spikes that are synchronous coming from similar templates. Because the way it's built, it's an approximation of a template matching step. Circus SVD, on the other hand, is much better. I mean, those flat curves say that even if the templates are similar at 0 time lag, it will resolve the collision properly. But at least now, we can benchmark all those stuff. And again, for those pipelines, what we can notice is whitening, again, helps, meaning if we whiten the data, either globally or locally, the difference in accuracy between the data that would not have been whitened and whitened is boosted for the low SNR cells. So those two methods will benefit from whitening the data. Again, so this is to handle this. So it's a bit technical, but at least at the end of the day, all the steps will count and matters. How robust those two matching steps are to sparsity. Again, we can test everything now quickly with this pipeline. So it's really straightforward to generate various a particular pipeline and sparsify the templates with various criteria and assess how good those matching templates are. Wobble it's counterintuitive, but it's pretty bad when the templates are dense. It's better when the templates are sparse, and it's, I would say, fairly robust to the sparsification of the templates. Circus OMP, on the other hand, start to decrease quicker. Again, the runtime of those tools, OMP is really slower when the templates are dense, and it's still slower when it's sparse, but those two are. So when you go along this axis, so you sparsify. Those are small details, but at the end, everything adds up and matters. How does motion correction also affect just the template matching? So assuming I have my static recording that I'm filtering, removing the admin and whitening because I realize that whiten helps. If I have my drifting recordings corrected in the best manner I can think of these days, how will those two engines behave? Well, they behave okay-ish, but you have some losses already. And that's, again, maybe a push for the idea of, aforementioned by Charlie, of having something that will be aware of the drift, but we have some cells that are lost in the process. This is the difference in precision between what I would have had and, in the static and in the corrected cases, and I'm losing cells quite a lot. So I just need to be aware of that. So now, I don't know, in a sense, we went a bit into the black box and we started to dissect the optimal pipeline. So a spike sorting is this pipeline in a sense, and we started to implement some of those methods. Biased towards some pipelines, but it's easy to add yours if you want to implement your ideas in the spike sorting framework. And since the black box are now open, we can compose pipelines. And similarly to the motion correction, maybe pipelines are just a set of presets of choices that would have to be made. Spiking Circus 2, in a sense, is a pioneering spike sorter in the spike interface framework. It's a choice, like I use the match filtering here. The clustering is the one from Circus, and the template matching is the OMP SVD or Wobble if you want to be faster, but who cares? And the meta merging is something I didn't talk about today, but so that's a choice. Sam, in order to make a comparison, made 3D clue 2 with a different choice. So the peak detection is the locally exclusive one, 3D clue clustering, and the Wobble choice here for the template matching. And okay, so I don't want to advocate anything, but so I just, at the end of the day, this approach seems to be fruitful. So this is on the static recording. So kilosort 4, 2.5, Circus 2, 3D clue 2, kilosort 2.5, and in the static. So this is the static case. You don't see well the color. So this is the static. Spiking Circus 2 here, it's better than kilosort, but I don't want to say it will always be the case, but at least let's say it's in the same order. We can see immediately then when we have drifting data, even if they are corrected, there is a huge loss, but that was already shown in the paper we published last year, but like we are losing more than 2/3 of the cells, and even kilosort 4 is like losing a lot. So 3D clue 2 here is completely collapsing, but that's okay. But it's a choice that has been made. So by opening the box, we started to make advised choices, and this modular approach, I guess, will be fruitful. So it's not finished because clearly in the case of the drifting situation, two options have to be followed. Either template matching that will be aware of the drift, either working more on the meta merging step, because at the end of the day, that's mostly what kilosort did. It's to improve the way of aggregating pieces of cells that have been found, but it has to be concluded. So currently in Spike Interface, everything runs on CPU, but the speed is slower than kilosort, but it's still okay-ish. I would say it's doable. So, okay, so in this talk, I hope I convinced you that Spike Interface now is also something that can handle component for spike sorters. And at the end of the day, we hope it will be able to really create full spike sorting pipelines to benchmark all those steps properly along the path. Spiking Circus 2 are work in progress, and we'll make a paper out of it quickly. But the idea is that at least we can advocate for all the choices. For the drifting recordings, we still need to benchmark the meta merging. and that's it. And yeah, the idea is to really push forwards in the community to contribute. So if you have your ideas, you can easily port them in Spike Interface in those components to test them quickly. And maybe your contribution will be only on the template matching, on the clustering or something, not on the full pipeline, because those full pipelines are now really complicated recipes, but at least every ID counts and it's worth trying it. And also the legacy usage and the interoperability of a framework. So if Yas, for example, was an example of a sorter that was dying even before being used, sometimes because of the language used or the fact that the postdoc disappears and so on and so forth. At least here the ID will maybe live a bit longer than the guy doing it and will benefit to the field for a longer period of time. So let's all improve the sorters also instead of the creation metric. So the two angle can be also followed. We can try to enhance the creation metrics to curate better the output, or we can also work all together to enhance the pipeline and the component themselves to, yeah, refine the stuff. So that's it. No, okay. Yep. Well, so first, okay, with synthetic recordings, you can generate the data according to your needs. So if you want to increase firing rates or the duration and so on and so forth, then I don't know, you can still, those benchmarks will allow you to provide plots of all the steps all across the ways. So I don't know, you can say or not, no. I mean, I don't have a way to know what's the best pipeline already. I would not do all those benchmarks. But I mean, you might have hints at least on where it's going wrong and where you should focus. But yeah, it's still work in progress in the sense that we don't know what are the key. So clustering clearly and template matching are the two steps where it seems that we are losing a lot of cells, even though the motion seems to be corrected in the best way we could think of those days. So this is already something that should tell us that there is some work that has to be done there. For the whitening, I'm not showing it here, but like also, so local or global doesn't matter. Regularization of the whitening matrix is something that's done in EEG field. And there is and it turns out that it seems to also benefits a lot. So those matrices usually are ill constrained and we don't take a lot of data to compute them. So we need to regularize them. That's also something that has to be benchmarked. So, but yeah, if you think that whitening is the key step, then at least you have the tools to easily make plots to compare.
Yeah, I mean, maybe not. One question, like, so like right now, there was, at least in the last workshop, some worries about reproducibility. Like, how do we know people are using the same software, and like, how do we make sure we standardize this? Do you think this approach, while it might be like the best algorithm, if like there's a lot of mixing and matching, that it'll make it harder to reproduce things across the class?
Yeah, well, at least you'll have stable blocks, then you can track them. I mean, for example, KiloSort 4 already comes in 8 flavors. You have 4, 0, 0, 1, 0, 2, and all those versions have different outcomes. So if you tell me I'm using KiloSort 4, yeah, but 4.0.6 was buggy and no one noticed it. And if you benchmark them, it's already there are flows. So it's not perfect, but at least those blocks, the idea is that they should be stable enough at some point and mature enough such that we can say, okay, this preset is this block, and this blocks. Yeah, I guess at the end it will benefit for the producibility and the tracking of the errors.
But we put up like.
Oh.
Where's it gone?
Bon, mais je vais y arriver.
Just running through the cloud.
Bring it. I don't know why is it.
Oh, here. I wanted to
So we have two questions in the Zoom.
got them here. Also.
So in the Zoom, there is a question asking if Mountain Sort 5 use a template matching method. No, not that I'm aware of. No, it's kind of a huge ISO split clustering on the clusters.
Some kind of matching, some kind of train, some kind of model to make the.
But if you look at the paper we published in the comparing the collision, it will go into the so-called clustering based only solution, and it was really bad at recovering the collision. And when talking about drift in simulation, we often refer to drift within a single session. How would you approach chronic drift generation and tracking, please? Yeah, that's a good question. No one knows properly, although Charlie showed a bit that within session, you might apply the same method and find units that will be stable. But currently, it's true that we don't address that. We mostly talk about drift within session and within a single continuous recording. This problem is already not properly solved, so we don't extend that to several segments. Yeah, we know why they are getting lost, actually. It's because the cringing, and so the way those stuff are done. So the cringing will never, I mean, if you have a cell moving further away from one electrode and going to the next one, for a while, its amplitude will be half of the two and will be decreasing before re-increasing. And if you look at those data, you'll see that actually, yeah, the amplitude of the wave, the spikes that are corrected have some pattern following the grid layout. And that's because of the cringing and the fact that it doesn't really interpolate. And well, we can talk more about that in details, but yeah, this is an issue. And that's why KiloSort 4 or some of the methods at the end are patching the stuff by trying to combine. But clearly, template matching, being aware of the drift would be, I guess, better.
Sorry, last slide. Do you have any plans to like integrate benchmarking these components like a spike forest approach?
So this is an ID. I wrote that down as a small project for the hackathon, but don't know. But now, yeah, Spike Interface can generate all those data on the fly in lazily and at no cost. So we could farm some sort of test suite and comparing sorters. Why not? We can also now, thanks to Alessio's work, generate hybrid recording in Spike Interface. So if you have real data, estimate the motion, create some fake templates, inject them, and compare that. So that's also something. But Spike Forest is dead. We could think about doing something else, but it's just a matter of resources also. We need to have some devoted CPU time to launch everything.
Spike Forest and new branch of the tree, so it's complicated. At the moment, the bet is generate a fake drift control and then now it's fake completely. The Spike Forest stuff was before the drift war.
But we have very nice Spike Forest website and change that stuff. The data set, the file and
So we should stop now. Just before stopping, we have one question for Charlie in the Zoom. Maybe Nina, you can.
Yeah, so the question is, which cases is it train your position?
the ball.
Oh, it's not like that's Alors, it's really, you know, very huge.
The neural net denoiser. Okay, so
Well, it's done
the way
The
the way
training
we
training.
have been doing it is mostly using previous sorting templates. So templates that you got from a previous sorting and then adding noise to them. But we're also working on some fully unsupervised approaches now that you can just like throw a recording in and train a neural net in 5 minutes for your new data, which I think is promising. So, but mainly right now we use like a known template library, which is a pain and a big problem, I think.
Merci.
Right. Those quality, there's enough. There's 4 people here that.